moving on. In this lecture, we're going to start chapter 19 on electrochemistry. In electrochemistry, we're studying reactions that either produce electrical energy or are driven by electrical energy. And at the heart of electrochemistry is the redox reaction. Remember way back to last semester, a redox reaction is a reaction that involves the transfer of electrons. Okay, so in a redox reaction, electrons are going to move from one thing to another. So let's review redox. Now, oxidation, remember, is the loss of an electron. Oxidation number when something oxidation numbers for something that's undergoing oxidation goes up. So the element's oxidation number will go up, become more positive. Reduction is the gain of electrons, and the oxidation number becomes more negative, or you could say goes down. Okay? So reduction, gain of electrons goes down because the oxidation number is becoming more negative. In this chapter, we're going to look at redox reactions in terms of half reactions. A half reaction is exactly what the name implies. It's half of the overall process. One half shows what's undergoing oxidation. The other half of the reaction shows what's undergoing reduction. So we'll write an overall process of overall redox reaction as an oxidation step and a reduction step. But remember that oxidation can't happen without reduction. Reduction cannot happen without oxidation. Now, even though these two processes are linked, one can't happen without the other, we can, in situations, physically separate the oxidation half reaction from the reduction half reaction. And we do this when we want to derive energy out of the reaction as electricity. If we don't, the energy that's going to be liberated in the redox reaction is going to come out as heat. And heat's not nearly as useful as electricity. Okay? So we want to harness the reaction in a very specific, the energy from the reaction in a very specific way. So we're going to learn how to write half reactions and how to use half reactions to get net ionic equations. Most of the processes we'll be dealing with will be given to us in what's called a skeletal reaction form. Okay? In a skeletal reaction form, we're given an incomplete reaction. The major components of the reaction are there, but not all of the things you need to complete a full net ionic equation. Okay? So, what we want to be able to do is we want to go from a skeletal reaction to a net ionic equation. So I'm going to run through the steps here. The first thing you do is you divide a skeletal reaction up into half reactions based on the elements that appear in on the reactant and product side. So if I had sodium plus chlorine going to sodium ions and chloride ions, then I would divide it up into sodium going to sodium ions and chlorine going to chloride ions. Okay? Next, we want to balance the number of each type of atom listed in each half reaction. So sodium going to sodium 1+, so there's one sodium on both sides, two chlorines in the chlorine molecule, so I have to have two chloride ions on the opposite side. Some half reactions have oxygen and hydrogen appearing in them that don't appear on both sides. So you always balance out oxygens by adding water, and then you balance out hydrogens by adding H+. Don't worry, I'll show you an example. This one doesn't have it. electrons to balance out the charge on both sides. So sodium going to sodium 1 plus, I need to add 1 electron on the product side so that the sum of the charges on both sides are 0. For the chlorine, I have 2 chloride ions on the product side, so I'm going to add in 2 electrons on the reactant side, so I have a -2 charge on both sides. Okay, note at this point you can identify what's undergoing oxidation and what's undergoing reduction. Okay, oxidation is the loss of electrons, so sodium is very obviously undergoing oxidation because the electrons are on the product side. Chlorine has to be undergoing reduction. Okay, that should be obvious because the electrons are on the reactant side. Now, our last step is to multiply one or both half reactions by an integer to make the number of electrons in each half reaction the same. In what we've got, the first half reaction, the oxidation half reaction, involved only 1 electron, a sodium going to a sodium ion plus an electron. So I need to multiply that one by 2. So if I multiply by 2, I get 2 sodium atoms going to 2 sodium ions and 2 electrons. Lastly, once the number of electrons are the same for the 2 half reactions, you add them together to get your overall net ionic equation. So when we do this with this example, 2 sodiums plus a chlorine molecule goes to 2 sodium ions and 2 chloride ions. And that's our net ionic equation. Now, let's look at something a little bit more complicated. I have MnO4 1 minus plus an iodide ion going to MnO4 2 minus and an iodate ion. Okay? So let's run through doing this one. I'm going to write it on the board here and we're going to walk our way through. MnO4 1 minus plus iodide ion going to MnO4 2 minus plus the iodate ion. All right, guys, let's work our way through. First thing I'm going to do is I'm going to divide this into 2 pieces based on the, well, here, maybe I can type this faster than I can write it. Let's give it a shot. Okay? So let me work on the computer here and type this in and see what we get. Or did I have? Oh, I was afraid of that. No, I'm going to have to do it on the board. I'm sorry, guys. It'll take me forever to type that in, and you'll just get bored listening to me type. Okay. Now, I'm going to break it up into half reactions based on the elements here that aren't oxygen. So I'm going to have MnO4 1 minus going to MnO4 2 minus. And then in my other half reaction, I'm going to have the iodide ion going to the iodate ion. Okay? Now, first thing I want to do is I want to balance out elements. Well, in this top one, 1 manganese, 4 oxygens, we're good. Down here, I have 1 iodine, that's fine, but I have 3 oxygens here. So on this side, I'm going to have to add 3 waters. Okay, I added in 3 waters. Now when I added in 3 waters, that means I have 3 oxygens, but I now have 6 hydrogens, so over here, I'm going to add in 6 hydrogen ions. So I added those in. So now all my elements are balanced. The next thing I have to do is balance charge. Here I've got a 1 minus charge, here I've got a 2 minus. So up here, I'm going to have to add in 1 electron, because a -1 plus a -1 gives me -2. Okay? In our bottom half reaction, I have a -1 charge here, a -1 charge here, but a +6 charge here. So right now, I'm up +6 on this side. So I'm going to need to add in 6 electrons. Okay? So that I have a net -1 charge on both sides. Okay? So there's my 2 half reactions. Now I want you to notice the top half reaction involves 1 electron. The bottom half reaction involves 6 electrons. So let's start fixing things. Before I can add them together, I have to have the same number of electrons in both half reactions. So I'm going to take this top half reaction and I'm going to have to multiply it by 6. So that means I'm going to have 6 MnO4 1- plus 6 electrons plus an iodide ion plus 3 waters going to 6 MnO4 2- plus an iodide ion plus 6 hydrogen ions and 6 electrons. I took everything from the reactant side and wrote it on the reactant side, everything from the product side, wrote it on the product side. Now notice, 6 electrons there, 6 electrons here, they cancel out, okay? So that leaves me with 6 MnO4 1- plus an iodide ion plus 3 waters going to 6 MnO4 2- plus an iodide ion plus 6 hydrogen ions. That's a net ionic equation. It's not a full equation, it's a net ionic equation. Now, the other reaction we're going to look at is silver ions plus a nitrogen monoxide going to silver the element and a nitrate ion. Okay? So let's look at this one. Let's erase. So, I'm going to start out by dividing it up into silver 1+ going to silver and nitrogen monoxide going to the nitrate ion. Now, silver elements are balanced, 1 nitrogen, 1 nitrogen. I've got 1 oxygen here, I've got 3 oxygens here, so I'm going to have to add in 2 waters. That means I'm going to need to add 4 hydrogen ions here. Okay? Now, this has a 1+ charge and there's 0 charge here, so I need to add in 1 electron. Down here, no net charge here. I have a net charge of -1 plus 4 plus 3 here, so I need to add in 3 electrons here. Top reaction involves 1 electron, bottom reaction involves 3. So I'm going to multiply that by 3. So that gives me 3 silver ions plus a nitrogen monoxide plus 2 waters going to 3 silver atoms plus a nitrate ion and 4 hydrogen ions. The waters are going to, the electrons cancel out. Now, up here on top, the silver ion gained an electron, so this is reduction. Down here on bottom, we have electrons appearing on the product side, so this is our oxidation. So I have my reduction half reaction, my oxidation half reaction, and I have my net ionic equation. Now, these are kind of tedious. There's a method to the madness, because we like to break problems up into half reactions, because that helps us decide how we're going to build our devices. Okay? So the half reaction method is important for us as we look at developing redox chemistry. It's going to be essential information in helping you decide how to build an electrochemical cell. Okay? And what's going to be happening where. So, NAD redox reaction can be thought of as the sum of an oxidation reaction and a reduction reaction. And what this tells us to do with our half reaction method is to mix and match half reactions to make things happen to get the kind of energy that we want out. Atoms and charges on both sides of an electrochemical cell in both half reactions have to be conserved. Electrons lost in one half reaction are gained in the other half reaction. And although the half reactions are treated as separate entities, the electrons lost and gained, the electron loss and gain goes on simultaneously. Okay? Now, once we know how to split a redox reaction to half reactions, we're ready to look at building devices that involves electrochemistry. Any device that involves a redox reaction in electrochemistry is called an electrochemical cell. There are two categories: electricity producers and electricity users. A voltaic cell is a spontaneous redox reaction that produces electricity. Hint, delta G is going to be negative. In an electrolytic cell, you're using electricity to drive a non-spontaneous redox reaction, so delta G is going to be positive. Okay? So we have two kinds of cells: voltaic cells and electrolytic cells. No matter which type of cell you're building, it's always going to contain some common elements. A electrochemical cell always has to have two electrodes used to conduct electricity between the cell and the surroundings, called an external circuit. It's going to have electrolyte, something that's going to conduct electricity in solution. It's got to have an external circuit. Okay? And when we draw electrochemical cells, the oxidation half reaction is always shown on the left in the representation of the cell, and the reduction half reaction is shown on the right. Okay? So you think about losing electrons before gaining. They're going on simultaneously, but as we read an electrochemical cell, we always put the oxidation on the left. Okay? Oxidation always occurs on the left-hand side at the electrode we call the anode. Reduction always occurs on the right-hand side in our representation at the electrode called the cathode. Electrons always flow from the anode to the cathode in the external circuit. Now, here's a representation of a voltaic cell and a electrolytic cell. Both are electrochemical devices. Okay? Anode, always on the left. Anode is where oxidation occurs, cathode on the right. In a voltaic cell, we actually have to have separate chambers for the oxidation and the reduction half reactions, because we're forcing the electron transfer through the external circuit, which is going to be some kind of device that needs electricity to power it. So a radio, a cell phone, your car, a flashlight, a hearing aid, a watch. Okay, that's going to be your load. And this is a spontaneous reaction. Energy is going to be released from the system. All right, the basic layout. In an electrolytic cell, anode again is on the left, cathode on the right. Doesn't have to have two separate chambers because this is a non-spontaneous reaction. There is not going to be any spontaneous electron transfer in the solution. We have to use a power supply to force the reduction at the cathode and force the oxidation at the anode. Something else I want you to notice here is in the voltaic cell, the anode is negative and the cathode is positive. That's because this is spontaneous and electrons are being shoved onto the anode faster than they can move out. And they're being pulled off of the cathode faster than they can be supplied. Okay? Over here in the electrolytic cell, the anode is positive because electrons are being forcibly pulled off the anode. And the cathode is negative because electrons are being shoved on, and they get shoved on enough, the thing down there that's supposed to take the electron goes, okay, I'll take it. Okay? But oxidation always occurs at the anode, reduction always occurs at the cathode. So notice here, X goes to X plus an electron, and the reduction electron plus Y plus goes to Y. Now notice over here on the electrolytic, it's A minus going to A and B plus going to B. Okay? So here I'm taking something that's not charged and making something charged, taking something charged, making something that's not charged. Here, not a charge going to not charged, charge going to not charged. Looks a little different. All right? Now, we're going to start off talking mainly about voltaic cells. Voltaic cells are our spontaneous redox reactions. So they're going to release energy. The oxidation half reaction and reduction half reaction have to be physically separated from each other so that we force the electron transfer to take place through the external circuit. The oxidation occurs at the anode, which is negative. Reduction occurs at the cathode, which is positive. Electrons flow from the anode to the cathode through the external circuit, and the voltaic cell has to have a salt bridge, also called a liquid wire, to complete the circuit. So if you look at that picture that we were just looking at, this is a salt bridge, okay, or we could refer to it as a liquid wire. And what it does is it allows the completion of a circuit. Remember that electricity doesn't flow unless there's a complete loop for the electrons essentially to run around. Okay? So if there were no salt bridge, the voltaic cell wouldn't work. There would be no production of electricity. There would be no reaction happening. Okay? The salt bridge allows current to flow by the movement of charged particles. Okay? And we're going to put particles in the salt bridge that can move from one side of the salt bridge to the other. Okay? All right. An electrolytic cell is non-spontaneous. The two half reactions are not separated. because without the flow of electricity into the cell, no electron transfer will take place. Oxidation occurs at the anode, which is positive. Reduction occurs at the cathode, which is negative. Electrons flow from anode to cathode through the external circuit because of a power supply. Okay? Now, notice the following. In the representation of electrochemical cell, the half reactions that occur at each electrode are written underneath the electrode chamber, or the electrode chamber, and the overall reaction is written in. I skipped too fast. Okay? Also in the representation of cells, the electrodes are labeled as to whether they are anode or cathode. The charge is shown. Ions are listed in compartments. Direction of electron flow is shown, and components of a salt bridge are going to be shown. So let's look at this voltaic cell. Okay, let's talk through this. All right, what we've got here is a voltaic cell with zinc and copper. And our half reactions are zinc going to zinc 2+, plus 2 electrons at the anode. And at the cathode, I have copper 2+, picking up those 2 electrons and becoming copper. So that the overall reaction is zinc plus copper 2+, going to zinc 2+, plus copper. Now, zinc is the anode, and it's negatively charged. Electrons are flowing from zinc, in this case through a voltmeter, which is our external circuit, into the copper electrode, which is our cathode, which is positively charged. Okay? Zinc, the metal, is called an active electrode. And over time, the zinc is being converted to zinc plus 2 ions, so the electrode, okay, zinc's coming off, becomes zinc plus 2. The electrode gets eaten away. This is called a sacrifice anode, because over the course of the reaction, the electrode is eaten away. It's sacrificed, okay? Copper here is also an active electrode. It's one of the components of the reaction, but the copper is deposited on. So over time, the copper electrode is going to get fatter, is going to get bigger. The active electrode here on the anode side is going to be eaten away. It's called a sacrifice anode. All right? And the copper zinc voltaic cell is essentially the first battery ever invented. Now, if we were to place the copper electrode in the cell we were just looking at with a different material, it wouldn't affect the running of the voltaic cell. We just end up coating whatever metal we put in for our electrode with copper. Okay? If, on the other hand, we were to remove the zinc electrode, you would have another story altogether. Zinc is a reactant. So if I remove the zinc electrode and tried to place it with something else, the reaction would probably stop, or you'd have a different reaction. So an electrode that is not a reactant or a product is called an inactive electrode. An electrode that is a reactant or a product is called an active electrode. You can always replace the cathode in a voltaic cell with an inactive electrode, but the anode is much trickier. You have to pay strict attention to what the reactants are when you're building a voltaic cell to see if you need an active electrode on your anode side. Okay, now let's look at this voltaic cell. Now here we have the reaction iodide ion, 2 iodide ions going to iodine on the anode side, on the oxidation side, and MnO4 1- plus 8 hydrogen ions plus 5 electrons going to manganese 2+ and 4 water molecules on the cathode reduction side. Now, when I look at my anode half reaction, I've got iodide ions and iodine. There's nothing there that I can build an electrode out of. Nothing that's an electron conductor. Iodine is a non-metal, it's an insulator. So in this case, I'm going to use an inactive electrode as my cathode. Carbon in the form of graphite is the cheapest, most common inactive electrode. If I look at my reduction half reaction, again, I have permanganate ions and manganese ions and water, nothing I can build a electrode out of. So we're going to use an inactive electrode again. So both of the electrodes in this voltaic cell are inactive electrodes. Now, I want you to look up here at the salt bridge. Potassium nitrate is in the salt bridge. You can actually take a glass tube, okay, put a salty jello in there that has potassium and nitrate ions in it, and it would work as a salt bridge and the jello won't come spilling out. You could also take that glass tube, you can fill it up with a concentrated potassium nitrate solution, and you put essentially glass fibers, okay? We call it glass wool or glass cotton. Plug up the ends in that, and the water won't come out when you put it like this, but it'll allow the ions to move, okay? Now, the interesting thing, or the thing to note here, is that the cation always moves toward the cathode compartment, and the anion moves toward the anode compartment. So cation in the salt bridge moves toward the cathode, anion in the salt bridge moves toward the anode. And guys, this makes good sense. Okay, that's where anions and cations got their name, from the direction that ions flow toward those electrodes. So the cation moves toward the cathode, the anion moves toward the anode. Remember, you're pulling electrons out here, so you need to bring negative charge over to here. You are shoving electrons in over here, so you need to move some positive charge in to meet it. Okay? So that's a full voltaic cell representation. Now, drawing a picture every time you want to talk about a voltaic cell seems a little wild. So the next thing we're going to talk about is cell notation. I'm going to stop right here because my battery's almost dead.